Okay, so we're talking about metric spaces, but now in a more applied sense. So we're going to try to use the idea of metric spaces to prove theorems. And number one theorem is, number one definition, number one concept is the limit, and number one theorem is that the limit is unique. Okay, so we defined it, and we have a general idea how we're going to proceed with this. But before we do that, here I made a bit of a detour just to connect the idea of the limit in the one-dimensional case, calculus 1. Okay, so a sequence of numbers converges to another number. Okay, so is it possible to converge to two numbers? That picture suggests why it is not, because the tail of the sequence has to be contained in an interval, and the intervals I'm referring to are here. It would have to be contained in that little interval around that point. If there are 2 points, you take those two intervals small enough and that they don't overlap, and the tail cannot be simultaneously contained in both of them. Okay, so that is why that's how we prove that there is only one limit in calculus 1. Now we're going to have the same idea for spaces such as R2, example below. You have disks. You have 2 points on the plane, and once again the limits are discussed in calculus 3, limits of sequences. Okay, it's a sequence of points in the plane. Okay, and so once again, why there is only one limit? Well, there you go, because you can separate the 2 points by two disks that don't overlap, and once again the tail has to be contained in one of them, but cannot contain in both. Okay, so that general idea is now will be translated into the idea for metric spaces and the proof as well. But first, just a short discussion of the balls. These are dimension 1 intervals, dimension 2 disks, dimension 3 balls, and then the word ball then is used continue to be used in higher dimensions. And so there are n-dimensional balls in n-dimensional Euclidean spaces. Okay, and then it also appears then in a metric space. Okay, so that's at the bottom. Given metric space, an open ball is those points that lie within less than distance or units from that point A. Okay, so that's the definition right here. Okay, so examples are in addition to intervals in disks. That's kind of an arc of a circle, if X is a circle, with that metric that we have discussed. And what else? Sphere, it will be this. What is it? Is it like, what is it? What do you call it? What's on the right? Cap? Yeah. A cap, yeah. So it could be small. Our main interest is small ones. Okay, but so then they actually look like almost flat. Okay, so and now taxi cab matrix produces very interesting unexpected balls, and that turns out to be their squares. Okay, so so that's the point 1, 1, and in pink is the ball around it. So, by the way, there is a taxi cab matrix in dimension 3 or any higher. Okay, and you once again can ask yourself, so that will be the homework to think about, taxi cab in R3 and its balls. Okay, so what a ball will be, what does it look like in dimension 3? So once again, well, first of all, you have to think of what the metric looks like. Well, easy to guess, right? So there will be an extra term over here. And then what the ball looks like. Okay, so what else? Okay, there's one more example of metric space that needs to be discussed. That structure, the topological structure of a metric space. A metric is that function, but then it creates a lot of structures on that set, and one of them is in what we call is the topology, and those balls are made of. Okay, so graphs now, weighted graphs. and we know their metric spaces. Okay, so say A, B, C, D, E. Okay, 1, 2, 1, 2, 3, 1. Okay, so for example, then let's look at the balls. A ball round A of radius 1/2. What is it? An open ball. All points within 1/2 from A. What are they? What? Like a cone? No, I don't think so. You see, there is no. This is not. This is a graph, so it is not containing anything. It is based on a set of these 5 elements. So x is equal to A, B, C, D, E. It will be A, that's right. The answer is A. Okay? Because the edges are only, it's data. So they only indicate the distance between the two adjacent elements, but there are no other points. So whatever we're talking about, a ball will be entirely, has to consist of the elements of the set. Okay, so it's A, and even distance 1, it is still A because there is because B is 1 unit away, so it is larger than. So it is. Yeah, it's supposed to be strictly less than 1, so that it's out. And then you might have to look at furthermore. Say, let's say, how about 4? 4. B. Well, first of all, A. B, E, anything else? C, anything else? Let's see, no, the distance to D is actually, what's the distance to D? 4. What? No, it does not. It shouldn't be. It shouldn't be. It depends. So you take the shortest one. It is 1, 1, 1 to 1. It is 4. It's still not there. Okay, so that's it. But if you take 5, then yes, a 5 will be A, B, E, C, and D. So in other words, the whole thing. It's possible that you get the whole thing. Okay. So as you can see, that's that idea becomes the word ball is not descriptive anymore. Okay, so back to the uniqueness of the limit. So this is let's take another look at to refresh our memory about. So this is, by the way, weighted graphs. The definition of the limit. Where is the definition? The definition of the limit. So right here. Definition of the limit based on the distances. Okay, so gx and a goes to 0. Okay, the illustrated on the left. So we're going to take that definition and prove that there's only one. Okay, so let's repeat the definition. So definition x n converges to a if dx and a converges to 0. Okay, so in metric space xd. Okay, so that's the definition, and a is the limit. Okay, so what we're trying to say is, that's our theorem, the limit is, well, I don't want to use the limit. There can be only one limit. So no more than one for a sequence. Okay, so we already have all these illustrations. So like this, if this is A and this is B, well, it cannot be the same sequence. Ultimately, they will be separate from each other. But before we proceed, let's put it in a more positive way, as we have in the past. We have when we dealt with the issue of uniqueness, we had a way to state it in a positive way, rather than there can be only one or no more less one. How did we do it? What does it mean that there can be only one limit, no more than one limit? What does it mean?
That it only converges to one point?
Well, that's just the same, the different wording is the same statement. It has to have different logic, and it will help us then to understand how we're going to prove it. So. We did it before with, what was it? I don't remember, but it did come up early in the semester.
Can you do it by breaking up the left and right?
No, you're thinking about proving it, but what is the logic? What is it is a loose statement. There can be only one limit for a sequence. It's the same word, yeah.
So what are we trying to do?
I want to restate this in a logical way.
So like
for any sequence. Okay, let's start. For any sequence, xn. Okay, then what?
There exists.
What? There exists what?
One and only one limit.
No, even first of all, there might be no limit to begin with. You have to actually say that what if there is. You cannot say there is. Because some sequences have no limits, right? So you cannot say that it does, it has to, because it doesn't. So. Well, what?
There may exist.
There may exist, but that doesn't say anything. The way it's the same is to say that there is a sequence. There may exist means that there is a sequence with a limit. Okay, there. So it is possible for a sequence to have a limit, which means that there is one sequence for which the limit exists. So it's not this. It's not a question of existence. So existence is we put it aside because we know that sometimes it does not exist. So we're not worried about that as long as we understand that we're discussing whether or not the concept is well defined, and existence is not to worry about it because it might not exist. But uniqueness has to be addressed, and it has a theorem. This proves that we are justified using the word "the" for the limit. Okay, so
We write it as an if then.
what?
We write it as an if then.
Okay, what if? If.
The sequence has a limit,
Okay,
then
what?
it is unique.
Unique meaning what?
The only limit.
Suppose there is a limit. Then A is unique. Unique means that it is there cannot be two. Okay, can you put this in logical way? There cannot be two.
If xn goes to A and xn goes to B, then A is equal to
Right,
B.
that's right. So it doesn't look that complicated, does it? And this is, as you can see, for any if, then it is a very logical statement. And the advantage is that we know now how to prove it. If we want to prove it, how do we prove it? Based on the definition and on the illustration on the left, how are we going to prove it? Well, same way as always when we're proving existence by contradiction. Well, I mean, it's not really much of a contradiction, but we are the logic is suppose there are A, and B. It's not really by contradiction technically. You just suppose that there is a sequence. We have a sequence, and it has two limits which may or may not be equal. We don't know that. And then we conclude that that they are. Well, actually, that we could do it, but actually, this particular proof is by contradiction. So we suppose. Well, so okay, we're still discussing the proof. So we'll suppose that A is not equal to B. A is not equal to B, which justifies the picture on the left. Okay, so we have A here somewhere, and we have B here somewhere. Okay, so they're distinct. What does it mean they're distinct? That they're metric space-wise. What does it mean they're distinct? Why is it important that they're distinct? Well, why is it? The idea on the left is once again, remember that idea that I suggested in the beginning, that they're going to be, we are able to separate them from each other in this manner. For a moment, if we think in terms of the two-dimensional space, we separate the 2 points by disks, and then we examine how can our sequence satisfy that inequality, that definition at the top simultaneously for A and for B, and it will arrive to a contradiction. Okay. But it is crucial that we are able to begin with. We are able to tell that these two points are apart, and that the structure of metric space is what we can restate. A is not equal to B. How do we restate that in terms of metric spaces? Two different numbers, metric spaces. We have like 3 lines of the definition. Contains only 3 lines. So 2 points are different. What does it tell us about the metric? Axiom 1. Well, we're still talking about the. We were just doing the discussion, the analysis of the proof. So it's okay to invoke some ideas that are not exactly absolutely follow from the axioms. We're just what intuition tells you. Well, I hope it's telling you that the distance between them is positive. Okay, so it's because the axiom 1 says that we have distance equal to 0 only if the 2 points are the same. And so we assume that they're not the same, so the distance is positive. And that is why we can separate them, because this distance is a positive number. And then so the question is, to justify the picture, we would ask ourselves, how do we separate A and B from each other? Using this number D. I did the distance between A and B. Well, first of all, we use balls. These are the two balls, ball 1, ball 2, and then what balls? Well, first of all, they're centered at A and B. Firstly, and secondly, what's the radius? What should be the radius of those balls? Or circles or discs? What?
1/2 D.
1/2 D, right. 1/2 DAB, yeah. Okay, so this is my R and this is my R. And they're separated. So those will be touching each other, but they do not intersect. So that is the idea. And then once again, how it follows, they are separated, and eventually, based on that, the limit right at the very top, it tells us that eventually my sequence should be either it converges to A, so xn converges to A, so eventually xn is in B A R, okay, and then I have xn converges to B, so eventually xn is in A B R. That's a contradiction. Well, yeah. Okay, so that's an outline, the idea of the proof. It is not the proof yet, just the idea. So how little we actually need to use here. So we're going to flesh it up, and the thing that we're going to need first is actually what's at the end. So we got to make it more abstract, and so even though all the concepts are here, this part is certainly will need work. What does it mean that they're eventually in this disk? Well, that's not too hard, because we have we just have to look at the definition of numerical convergence, right? So xn converges to A is expressed in terms of the distance xn converges to, going towards 0. So we'll figure that out. But this is what I want to talk about first. Why is it a contradiction? So a sequence is eventually, or suppose that the whole sequence is in one disk, in one ball, and it is also in the other one as well. Okay, so why is it a contradiction?
Because the balls don't overlap.
Yes, because BAR, BR is empty. That's why, indeed. So the same thing can be contained in two sets that do not intersect, because that would be straight against the definition of intersection. Is there or is there not an element they share? And well, they don't. Okay. So, but do we know this for a fact? And the answer is no. At no point we have made that case. Because we define disks or balls in this manner, in these abstract metric spaces, then this is not an established fact. But it better be. It better be. If you have two balls and the distance between them is known, a positive, then they better not intersect. Otherwise it's certainly whether calculus or not. This is a kind of a geometry that you do expect for a metric space. So two balls intersecting with each other, of the radius equal to half of the distance between them should not overlap. So it's like this is not supposed to happen. So if my radius R here, this is A, and this is B. Okay, so they should not intersect. It doesn't matter what the shape of that is. We have seen different shapes. No matter what the shape is, they should not have some protrusions that would make them intersect, like this. Okay, so that's not supposed to happen, if logically speaking. So a circle with a circle, well, let's prove it. So we start with this. Well, let's call it a theorem. It is an important one. So XD is a metric space. What is it? AB belong to X. R is equal to 1/2 distance AB greater than 0. Then BAR, BBR is empty. Okay, let's prove it. We have not that's the good news in a way that we haven't had any theorems about metric spaces yet. So this will be the first one. So, which is good news because then we have nothing else to rely on but the 3 tiny axioms. So the proof is naturally how? When you're saying something is empty, how do you prove it? Yes, yeah. How do you prove it?
By saying it's not empty.
What?
By saying it's not empty.
Right. So by contradiction. You can make it specific. That's the advantage of some general statement, but fortunately its negation is not. So in fact it's non-empty, which means that there is an element there. So by contradiction there is some X that belongs to the intersection. Okay, so literally what I plotted there, so these are the two balls, and then there is an X over there. Okay. Okay, so at this point, we take these two and use them as, and use the definition of the ball. So X belongs to the ball radius R around A, which means what does it tell us about the distance? X and A. By definition, the distance is what? Less than R. Same thing for the other one. Distance X B is less than R. Okay. So do you see what I'm driving at? Let me try to make a suggestive picture here. So this is less than R, and this is less than R. What conclusion can we draw from this? Let me help you out. Okay, so what's the conclusion? What did that plot in green, what do we call it? In green? What?
Triangle.
It is a triangle. Okay, have you heard the word triangle recently? Yeah, triangle inequality. Okay, so let's use the triangle inequality. By the triangle inequality. Okay, what do we have by the triangle inequality?
The distance between X and A plus the distance between X and B
Yeah.
equals the distance between, or equal or greater than
B greater than or equal to D A B, okay, which is equal to 2r, right? And on the left, we use these two inequalities. They're less than r plus r, which is 2r. Right? A contradiction. Okay, so the only thing we use is to prove it is the triangle inequality. It's not like we have too many choices. It is the theorem is at its very beginning. The theorem of metric space at its very beginning. So we up until now all we've had have been the three axioms. Okay, so nothing else, and that's why when you're proving something, those are the only ones you are allowed to rely on, and that's what we have. But now we have we are at the next level. We have the three axioms and this theorem to be used. So instead of three choices, we have four. Okay. So and then we certainly know why we went this way. This is the idea of the proof. We know that these will not be intersecting, those two balls around those two supposedly distinct points A and B. Okay, so let's use the theorem and prove the other one. So proof of uniqueness. Okay, so we'll use this previous theorem as a lemma. Okay, okay, so let's take another look at the theorem. So here's the theorem. So suppose xn converges to A, xn also converges to B. Okay, so and then through and we assume that they are distinct. So that is the assumption. That's why we are talking about contradictions. We assume that they are distinct, and then conclude that the distance between them is positive. Okay, so that's the starting point. Let's write it up to begin with. So suppose, once again, just repeating the theorem pretty much, it's always a good idea. Xn converges to A, Bn converges to B. A is not equal to B. Now let's just do it one step at a time. Then distance xan converges to 0, and distance that's an x over here. Distance xnb also converges to 0. Okay, now suppose, one step at a time, once again, suppose A is not equal to B, then, so this one was by definition of convergence, and we'll get to that, but let's just say first that we're talking about the two distinct ones. So by axiom 1, we have distance. So R, we assign R equal to, define R to be distance between A and B, and it is positive. 1/2. Okay. Now, so why do we care about this R 1/2? In fact, let me. How about I put epsilon there? So it's also a good idea to connect it to previous proofs related to whatever. And in this particular case, we are dealing with limits, and we did proofs of limits with epsilon and delta in calculus 1. And so let's call it epsilon, because that's really what it's about. Where it's epsilon is going to reappear right here with these. We're now applying the definition of what? Of convergence of numerical sequences. These are two numerical sequences. So we know what it means for them to converge from calculus 1 or 2, and now we know what that epsilon is. So let me call it 1. So from 1 there is n such that we'll call it 1 and 2. Okay, so converges to A converges to B. There is an n such that for all n larger than n capital, dxn converges to 0, which means that it is simply that number. I'm sorry, this is xn A, xn B. Okay, number is less than epsilon. Okay, that's this is the definition. So definition of limit of numerical sequence. So by definition of a limit of numerical sequence, what does it mean for sequence of numbers? Distances are numbers, so those are 1 and 2 are numerical sequences. So what does it mean for a numerical sequence to converge to 0? It means that it's at some point it will be less than epsilon. What epsilon came from? We brought epsilon from the previous line. So A and B are not equal to 0, so that's how they close to each other is the standard of closeness is what we're going to use as epsilon, so divided by 2. Okay, so well, there you go. So we are at sooner or later, that is what means eventually. There is an n such that for all n larger than n. That's the technical description of that loose phrase, eventually. So there is an n such that for all n larger than n capital, the distance will be less than epsilon. Okay? Then from 2 is the same. So once again, using the definition one more time. This one is so once again, if we want to be careful, we're applying the definition twice on 2 different occasions. Epsilon is the same. It is in the beginning of the definition, so we can just put it forward as the same. But then this is different, possibly. That for all n larger than m capital, dx and b is less than epsilon. Okay. So, now let me try to make a picture. So this is, well, I don't think we need a, well, we didn't get to the, we didn't get to the disks yet. So let's, what we need now is the, that eventuality idea now translated to 2 statements need to be merged. So we need to merge these. Okay? So then there is, and say k such that well, actually that's not how I want to handle it. I want to merge these 2 statements together. And so which means that I have to make a choice between n and m in order for both of these two inequalities to be satisfied. How do I make them satisfied simultaneously? So I want these 2 statements right now are entirely separate from each other, even though both of them are using epsilon and all of that. But this is where the problem is. They refer to different parts of the sequence. Okay, one is longer than the other. So that is makes it impossible to just merge them together. That is why I have to pick the larger one. So I let, say, L equal to max m, n and m. Then for all n larger than L capital, what's going to happen is then if it is larger than L capital, it's larger than m, n is larger than m, which means both of these 2 statements are satisfied. Okay? So, and then I can write them side by side as one statement. So d xna less than epsilon and d xnb less than epsilon. And then we are almost there. We're almost there. we have now two sequences. This part is really not that important anymore. The beginning, the ending is what's important. Now we interpret this in terms of balls, right? So the distance of xn to a is less than epsilon. So xn belongs to b a epsilon, and xn belongs to b epsilon. Okay, but they are disjoint by the last theorem. The end. So you cannot have the same element belong to two disjoint sets. So that's the end of the proof. Okay, so so that proves the uniqueness of the limit, and it is the beginning of the theory of metric spaces, because so that is a sequence of convergence of a sequence, which is at its simplest. And now the language that we want to use, we can now use the limit of a sequence. But then limits can be used in order to define the limit, once again, of a function. So then the limit of a function, just as in calculus 1, there's at this point there won't be a lot of difference. And then limits of function. Then what's the crucial application of limits of functions? Number one will be continuity. The limit of a function so we can speak of functions continuous on metric spaces. So you can have function between two metric spaces. Well, let's just do it. Let me point it out quickly. So f from x to y, okay, xd y, say d capital. Well, what d capital? Okay, are metric spaces. Okay, and then f is called continuous. If what? Well, do you remember the definition of continuity from calculus 1? No, this isn't continuous, right? So does this little picture look familiar? So that is this function is not continuous, as opposed to, say, this one, which is. Okay, so what's the difference? The hint is you need limits to explain the difference between the two pictures.
Limit on the left equals limit on the right?
The limit on the left is equal to the limit on the right. There is one missing part.
The function at that point?
And equal to the value of the function at that point. Otherwise, you're going to end up with this. So even though two-sided limits are not equal, are equal, the function is not continuous. So that is a good definition for calculus 1 continuity, because there are only two ways you can approach a point, from the left and from the right. But seemingly, but actually it's not entirely true. You can approach the points from both directions simultaneously, like this. So alternate between left, right, left, right, left, right. So it doesn't have to be in terms of left and right limits. The point is that the limit itself should exist to begin with and equal to the value of the function. Okay, since we already have that language sorted out in metric spaces, I can just state it. So f of xn converges to f of a for all a in x and all sequences xn converging to a. Okay, so pretty much you can see, you can match these up. You can match these up to understand what's about. So you have convergence of inputs, and the result should be convergence of outputs. The idea of continuity is really quite simple in that sense, that you can see the function on the right, in the middle on the right, is not continuous. Why? Because even though you can easily think of a convergence of x's towards a from both sides, what's going to happen to the y's? Well, they will be jumping up and down wildly, and they won't have any convergence. Okay, so that's why we define continuity in that manner. And as you can see, we need those three tiny axioms to have the whole thing sorted out in terms of continuity. But certainly there are challenges, and you can see how right away you have. I'm simultaneously invoking the two metric spaces, two matrices. So I'm using here. What I'm using here is d xna is going towards 0. That is the matrix D lowercase is in the x space, in the metric space x. In the meantime, over here I have D capital, the other metric from, what is it, fxn fa. This one is converging to 0. So it is, as you can see, our compact language of continuity in sequences. And metric space is certainly, if you expand it, if you really want to get to the bottom of it, there's quite a lot going on, even though, once again, everything is just so compact because the definition is so compact. Okay, so that's the continuity. You can talk about continuity. I wouldn't talk about differentiability if you want to continue on with calculus, because you cannot do calculus like that without algebra. So for the derivative, you need to remember, divide by you have to subtract values. So slightly different approach. In subtract values, you need algebra. Metric space has nothing but set and a metric, so there is no algebraic operations on these sets. So for calculus, you need more than that for the rest of calculus. And so that's why this is more typically called topology rather than calculus. It's just in calculus everything is kind of piled together. Because the numbers have all of these structures and they can be used simultaneously. Okay, so we'll talk a bit more about that next time.